Afternoon, everybody. I want you to take a look at the picture we have on the screen right now. And what does everybody see in that picture?
Liverpool fans are going home, maybe, after the win.
What do you see up in the picture? That's a bottleneck at the top. That's the answer there. So our talk is going to concern that, the bottleneck at the top. Thank you. I think that's in China, isn't it?
Yeah, it's in China.
Okay. So, our topic is healthcare outbound scalability topic. My name is Bruce Stevens. This is my associate, Sujoy Achara.
Hi, everyone.
We are from Cerner Corporation in the United States. We do healthcare information systems. That's what we do. That's totally do. We have different parts of the system there. I'm the director of the revenue cycle system, and my favorite sport is golf, but I also like soccer around the world too. Okay.
Myself, Sujoy Acharya. I work as a director and principal engineer. I have 15 plus years of experience in software development and design. My hobbies are basically soccer, and soccer. Okay, Bruce?
Yeah.
You wanna go?
We're going to tell you what we worked on. We had a problem in our software. We worked on that problem, came up with a high-level design for it. We made our first test on that, see how that turned out. Then we redesigned it, the system with Apache Ignite. Tested it again, did some more refactoring, and then finally got kind of like where we want to. I do want to say about the conference this week, it was a real blessing to come here. I felt like I learned a lot. And have a lot of good ideas to take back to our development area as we build our software there. So I said we are an application group. We build healthcare information systems. We do more the application development, not the framework development. So in that respect, we learned a lot from the teams here and the different technologies available. Maybe it will flip. Maybe it won't. I have to get over here. There we go. Back too far. Okay. Maybe I got it. So let's talk about our issue here. We have a lot of places in our applications that we use in-memory computing. We're evaluating that and using in different parts of the system to speed it up and get the performance that our clients want. I want to talk about one particular use case we looked at in the system recently. Can you flip that one? I want to. I won't work. Sure. I'll walk around. I want to talk about the one place we use that, and that's our outbound interface there. And I will tell you what that is. Our registration system going into the hospitals, we have a scheduling system, we have a registration system, we have the patient accounting system. So as the patients go into this hospital and they schedule an appointment with the doctors and the physicians and register there, and this is an enterprise system for hospital systems that are very, very large, many facilities around the nation. They're coming into the central system. We need to outbound all that information to other systems in case they want to do that, a foreign system. We find that to be a bottleneck. Currently, our system can support about 25,000 transactions an hour going out. It's an outbound transaction of basically the patient demographics going out of the system. We have to collect that. We have to format it into a format called HL7. That's the industry standard for outbound information passing from system to system in healthcare. And we have to sequence those transactions in the correct order as they go out. So the system updates need to be echoed out. Each echo contains a large amount of data, and we have to keep them in sequence. So that's our problem space. As I said today, we get about 25,000 an hour. That's what we can handle, and that's big enough for the client base we have today, but we have bigger and bigger clients coming on the system there, and we project that we are going to need 90,000 transactions an hour to meet our need. Go ahead, Sujoy. About our product again, it's a healthcare information systems, usually primarily in the United States. We have a lot of hospital systems up on there, but we're also global too. Central America, Middle East, Sweden, we're around the world, but I think primarily we focus on the United States. Includes scheduling, registration, and patient accounting, your basic systems of your healthcare environment. That's our goal there, and that's what the revenue cycle builds there. Okay. As I said, the registration ADT system, admissions, discharge, and transfers, we have to send them out after the transactions happen and echo them out to foreign systems that need to get that information. Maybe it's a clinical system, maybe something in the hospital needs this information, so we send it out, and it has to be in sequence. About our platform, we are a Java shop. We have Java running on Tomcat. On the middle tier, we have a front end on a browser-based application. It's mostly a Microsoft SQL Server database behind that. We use a lot of JMS and other technologies out there. Back end, we have reporting systems running on Hadoop and whatnot there, but our transactional system, the heart of that system is such, that kind of system. That's what we are. So our challenge to scale out the outbound interface for larger clients. How are we going to do it? We thought about some options. We could tune the code and make it faster. We looked at that, and that really wasn't a practical solution to get that code down from like handling 25,000 records to 90,000 records an hour. We weren't going to just tune the code and get it that much faster. That wasn't a practical solution. We can scale vertical, just put a bigger server on there, put that in play. That wasn't going to do it either. We weren't going to get there, or at least not in a affordable fashion. We thought about executing the transformation sooner. Could we build this data quicker, sooner, somewhere upstream, so we don't have to do this work at this point in the flow? That didn't seem right either. If we put it into the registration activity directly, it would slow down the registration UI and cause the response time to those users to be slower. Plus, the functionality belongs more in our back-end part of the system that is doing this work. We really didn't want to mess that up. So, simple approach, we want to process these in parallel. We get these records coming in here. The transformations, they don't have to talk to each other. The information just has to be reformatted for each transaction, rebuilt, and then sent to the system. The sending the data out through the FTP pipe and whatnot, that was fast. There was no problem there. It was the transformation of the data that was spending all the time. So the simple design simply was, we're going to take these records, get them in, send them out to a lot of different pipes through JMS, receive those messages, do the transformation, finish that, send them back to the central system, get the records, and pipe them out to the foreign system. Simple solution. We wanted to have a clustered, highly available solution so we could spread it out for scalability and high availability. The biggest challenge in this design we felt was the sequencing control. We need something to control the sequencing across these JVMs, running multi-JVMs that says, listen, I'm going to send you out, send you out, send you out, send you out. You're going to be running in parallel, competing on time, coming back to us, and we're going to send you out there. We just had to make sure when we got those messages back from the JMS systems and the consumers there that they were still in sequence and we can send them back in sequence. So that was the more trickier part of the code to handle that. How are we going to handle that sequencing? Okay, so high-level design. Any questions on where the problem space was? Okay. Yeah.
On a high level, can you give an overview of what kind of processing you did in these records?
It's a transformation. Take the record, they come in XML. They have internal data there. There's a standard format that goes out between system to system on hospital systems called HL7. It says the first field, it has a key value, patient name, and this is the format for it. When you put out like gender, there's a specification for how you put the gender out. Your address, these formatting there. So that XML we store internally in the system. We take it to the transformation system, we call it the OpenLink system there, that does this work there, and that's all been coded. And it's an older system, to be honest, and it's been working for a long time. And we didn't want to really rewrite the entire system, rebuild it, and start from scratch. It could be done. We could have redone the whole thing. But basically, we want to take that component of the transformation and rip it out of the engine that ran in sequence there, spread it out, do the sequencing, and then just bring it back and pipe it.
Thanks, Bruce. Thanks for the background. So this is our initial design. We created a microservice system. In our standard clients, we have 100 plus JVMs, basically. In big clients, there could be 200 JVMs. From any of these JVMs, patient data can change, right? Someone is logged into a system, is changing patient data, is associated with a JVM. So what happens when the patient data is changed? For example, maybe you are admitting a patient. Maybe you are transferring him. Maybe you are changing his name, admission time, address. Any information you are changing, we are sending a JMS message back to an exclusive queue. Any idea what is an exclusive queue? we use TIBCO EMS. In TIBCO EMS, there is a provision of having an exclusive queue. Exclusive queue means there is always a dedicated consumer. When that consumer goes down, then it selects another consumer, and that becomes its primary consumer. So when we send JMS message, in the message header, we send different informations, like some keys. Keys means patient location, where the patient is admitted, SSN number, driving license number, some other patient identifier. Why do you need it? Because some transaction need to be processed in sequence. Maybe they are related, they have to be processed one by one. So this sequencing is maintained by the single-threaded processor. So in our microservice, we have two components. First component is the blue one, message sequencer. It sequences data based on the keys. And in database, we have a couple of tables and store procedures. Using this big, long store procedure, it maintains the sequence. Now, once the sequencing part is done, next comes the OpenLink Adapter. OpenLink Adapter basically is a adapter unit which works with OpenLink. OpenLink is one of our messaging framework which communicate with all the other system, healthcare system. The operating protocol is HL7. So what happens when you are publishing a JMS message with header, it is coming to my consumer, then using the keys we are sequencing it, then sending it to OpenLink Adapter. Adapter is taking the XML information, it's converting it to HL7 and sending it to outside, out of the door. But I'm talking about sequencing. What is sequencing? Let's take a look at it. So this is sequencing. Suppose a patient is admitted to a hospital bed A, okay? So he needs to be transferred to some other bed because of his critical medical illness, maybe in ICU. And then his bed need to be cleaned up. Maybe patient B will be again admitted to the same bed. So now patient B's data should not go out before patient A's data, right? Because they are in the same bed. Once it is cleaned, then only the second patient can be admitted to that bed. We maintain this using two database tables. First table is called message status, where what happens, every JMS message comes with a transaction ID. We log that transaction ID, and right now we support only 12 keys. We talked about keys, right? One key could be patient location, SSN number, driving license. So only 12 keys are supported, along with the status. Status means whether the transaction is being processed or waiting or failed, the status. And also, there is another table called message key. In message key, we store the key information. This is just a projection of the first table. For example, if a transaction has only two keys, maybe patient location and SSN number, then two rows will be inserted into the second table for the transaction. Now explore the sequencing example. So suppose first patient is coming with only one key, key 1. The key 1 is bed 001, from where he will be transferred. So what do we do for sequencing? We first check in database whether that key exists, okay, using a SQL store procedure. So if that doesn't exist, in this case it doesn't exist, so what will happen, one row for that transaction is 3001, will be inserted in the first row with the status processing. And this request will be sent to OpenLink Adapter for transformation, XML to HL7 transformation. And another row will be inserted to message key table with the key information. Now, an unrelated transaction is coming. This is not related to the first patient. Maybe some patient is getting checked into bed 999. So what will happen? It will check again to database and see whether that key bed 999 exists or not. Here it doesn't exist. So what will happen? Again, it will be sent for processing. One row will be inserted into the first table, message status, and one row will be inserted into message key table. Now, the second patient is coming into the picture. He is coming with same bed ID, bed 01. What will happen? We are again checking it. It exists. So this record should not go out. So it will be in waiting state. And one row will be inserted into message key table as well. So after that, when the first record is processed, first information is sent out of the door, this information will be removed from the message status table and message key table, and in turn, it will find the oldest transaction for each key waiting for this. In this example, we have only one key, First key is bait 01. For that, only transaction 3 is waiting, right? So it will release transaction 3, and transaction 3 will be processed in turn. So now take a look at the big design, how different components are laid out. So this is our big diagram. You can see 7 queues are being used. The green component are the Java component, microservice component. First component is sequencer. It works with the DB and SQL store procedure. Second component is called OpenLink Adapter. This OpenLink Adapter is not single-threaded. So it has 16 thread with the hub that transform XML to HL7. So parallel 16 unrelated transaction can be processed faster. So when a new transaction comes, this many messages flow in the system. Very simple, right? So we deployed this design to our clients. Any guesses? What was the output? It was 25,000 earlier. After moving this to microservice architecture, what could be the throughput?
65.
Man, 65,000. So we are happy. Oh, we have 65,000. But our big clients like Northwell is one of the big clients. Big client, it could be around 100,000 or could be 90,000 at least. So how can we achieve this? So we went back to our drawing board and tried to find out what is going wrong. So we found that every minute we get at least 50 dB blocking. So if you look at the flow again, so what happens? A JMS transaction is coming, we are checking, hey, you exist or not. Then we insert into a database, and if it if any existing key is there, it will wait. Otherwise, we'll send it for transformation. During transformation, if it fails for some reason, maybe connectivity goes out or some XML format issues, then the status should be marked as failed. Again, a database transaction. If it succeeds, then it will remove itself and also the oldest 12 transactions which are waiting for this guide. So they will again be echoed out. So here, these are the 4 database access component which is basically slowing down our process. If you look at here, we have 3 long stored procedures, huge monsters stored procedures. One inserts data, before insertion it checks different things. Second one is check candidate message. Third one is for removal. And fourth one, when something fails, it just updates the SQL. So how can we, get the 90,000 transaction record, just bypass these database things? What would be the best approach? Maybe we can move everything to cache, right? Move the computation directly to the data. So we thought of moving everything to Ignite SQL. Okay? So we already talked about 2 database tables. One is message status and another one is message key. So all the fields we annotate with Ignite's query SQL field, index them. Sometimes we set affinity keys as well. And then we configured 2 caches. Like one is for message status and another one for message key. And then we converted all the stored procedure to Ignite SQL. So first take a look at how dependency check works. Dependency check SQL is really simple. We're just querying the message key, whether any key exists. If the result set size is more than 1, we say that, hey, there is a dependency. Insert query, again, we are first checking dependency. If any dependency is there, we are changing it to waiting. Otherwise, we are changing status to processing. And then for each key, we are inserting rows into the cache. For remove, again, we are directly removing from both the caches and finding oldest keys for all the transactions using Ignite SQL. And after that, we wanted to make sure that database and cache operations are really matching, whether any flaw in our Ignite code. So we kept both the data access object. Like first one is the message status DAO, you can see in blue, which is interacting with the database. And second one is message status cacheable DAO, which is interacting with the cache. Both the cases we measured time and we created a logger where it logs in CSV format. First logs the operation, what type of operation it is, then the transaction ID, time spent in database, time spent in cache, and the reference, something like this. So still, we found that it was not scaling up to 90,000. It was going around 68, 70,000, not
Yeah,
beyond that.
we still weren't there. We shifted it over to a cache, but it was still a SQL cache hitting it that way, and we still found out it was still not getting where we wanted to. Now, if I'd gone through this course the last 2 days, I'd probably be quicker to figure out what we could do optionally there. But we looked at that and said, let's flip this algorithm a little bit. We think still hitting like a SQL approach isn't right. Maybe a simpler approach with a key structure would just be a lot simpler. Put these structures in a key and just run them there. Use the cache, but more of a key structure, and hit the key structure a lot faster. We could close the gap.
Right. Yeah. So we refactored our code and thought of just removing the Ignite SQL and go over with JCache and only key value pair. Okay. So again, take a look at the algorithm, how it works. So we still have same cache, message status cache and message key cache. First patient data is coming with transaction 001 and same key page 01. So what will happen? Now it will check again in cache whether this key bed 01 exists or not. Doesn't exist, it will enter one key. The key would be bed number or the key value, string value, and the value is a set, hash set. There, all the transaction related to or associated with this key will be tagged into. For example, now in this set, there will be only one transaction, transaction 001. And another entry will be entered into message status, where the transaction ID is the key and the value is the message status object itself. Now the second transaction is coming, again, which is unrelated transaction. We are checking the cache for key bed 999. It doesn't exist, so another key will be inserted into the cache, both the cache. Now the third transaction is coming. Again, it has a dependency on the first transaction. It should not go out before the first transformation is done. So what we are doing is, transaction 003 is added to that set. So when first transaction is completed, it will be removed from the value of that key, and this transaction 003, this is the last transaction which is waiting in the queue. It will be processed. So this is how actually we designed, and after measuring things, we found that for database operations, 50,000 transactions, and there were up to 100 dependencies. It was taking 73 minutes in small servers like commodity servers. And CRUD operation took 42 minutes, whereas when we moved with IMDG solutions like key value pair of things, then the cache operation took only 3.5 minutes. But still, it was not 90,000. We tried all these things, still it was not 90,000. So again, we went back to our drawing board and tried to find out what is going wrong. We talked about transformation pipes, right? That transform XML to HL7. So we found that using 16 threads, it is not scaling up well. So how about adding 2,000 threads then? Can it scale, Bruce?
Yeah, I think so.
Yeah, but if you create more threads, the startup time will increase because these are TCP/IP connections. It will connect with the hub, and if something goes wrong, even the OpenLink will go down. So we actually tried an error process and found that 40 to 45 pipes, if we add, then the transformation works fine. So when we added 40 pipes, boom, it reached 90,000 transactions. This was our story. If you have any question, you can ask.
So when you say pipes as opposed to threads earlier,
Just because we use pipes a little bit more because we're going out through JMS and processing out of that one JVM and going around the system, let it work somewhere else and come back. So it's kind of the same concept as a thread, but since we're leaving the thread of a JVM and sending it out to a queue, and the queue puts it out to a bunch of JVMs sitting off of that and then processes it and come back, we would just call it pipes. But I think it's the same concept. Good question.
Does that include scaling up the Ignite part as
How big do we make the Ignite distributed cache? How big do we have to make that?
Number of nodes?
Whatever measurement you had to scale up to.
Yeah.
Nodes, RAM, whatever.
Right now, actually, in our PORF environment, we use embedded 3 instances, and 6 other normal servers. Since all the transactions that is coming are on-the-fly transaction, we are not storing anything because we don't have to store, because there is no meaning of storing old transactions. We already have left-hand side, we have our Sorian financial application, while in database we are storing all the information, historical information. These are just processing information. Processing is done, just throw it out.
So those 45 pipes all touch the same cluster, Ignite cluster?
No, what if they are not touching the cluster. If I go back again here, I can show you. So here, Ignite is playing role in the sequencer part, okay, in this green part. This is OpenLink Adapter. So when your sequencing is done, we are publishing a message to OpenLink Adapter. So from here on, it is taken care of. If it is related, then sequencing will take care of it. If it is unrelated, they will be processed in parallel. So now, earlier we had 16 thread, now we have 40. 2020 in both the instances. But if you talk about the sequencing Ignite instance, we have 3 embedded instances and 6 other instances. Yeah. Go ahead.
2 questions. The first one is, you mentioned you have 12 keys, and then, if I understood correctly, you flattened them down to 1 key in the key value solution. Does that mean that all the keys have separate distinct values?
Yes. So examples of keys. Let's say a real simple use case. There's the hospital facility. That's 1 key. There's the bed that the patient's in. That's a 2nd key. And then there's the patient identifier. They'd be the 3 basic keys, and we can grow on that. It could be the subscriber for a guarantor for a child. It could be several cases there. So 3 keys is typical. 4 or 5 is that. We just allow 10. In our design, we could have flattened that down to 1 key or 12 keys. It's 12 unique pieces of data there. It's a question of how we wanted to implement it here, how fancy we want to get.
The second one is, did you try using optimistic concurrency controls?
Yes, absolutely.
And you didn't scale it?
It didn't scale.
That's why we came here to London to learn.
To learn from you guys.
Okay. Okay.
Any more plans?
In work-wise, yeah, we have a lot of options in our business there. We have a client who wants results back on the UI for validating diagnosing procedure entries and see if they're going to be valid on their system there. They want that back in 1 second, and we got to produce a lot of work there. So we're putting a lot into the front end to validate there. We have, in concert with getting more containerized and going to Hadoop there, we have a use case where we calculate how much they're going to get paid from insurance companies. This is the United States, we don't have socialized medicine. This is the way it works. Do that, and every so often the hospitals go out there and say, what if we change this rate to this service from this much money to this much? We say in the contract, by the way, let's go fire that up and let's go run a year's worth of patients through the system and say, if we had this contract set this way, how would our revenue look like? And we want to fire that through there. So we want to scale that out with a scalable solution like Hadoop and Spark and probably Spark and let it scale out and do those calculations there. But there's a lot of reference data in that, the service amount and whatnot. And what we found out as we scaled out and whatnot, we don't want to have big JVMs inside the cluster. We want to keep them small. So we don't want to keep a lot of data inside each JVM. Hold that data as reference data. Say, I don't know if you guys are familiar with DRGs and APCs and other reference data there. It's basically the service code. So this service code is going to get paid this much money. That's our reference data. So when we fire that up, we want to keep that in memory and then run all those patients against that calculation and run that and get it done pretty quickly. We found out, that if we had little caches in all these JVMs and scaling it out, it was killing us on loading the cache every time we fired up a new job inside there, and it was taking up a lot of memory. So it really says get that out of there, move it to distributed cache, spread it out once in somehow to the cluster, and let it scale that way for that reference data. That's one of many things we're looking at for more distributed memory usage in the system there. Speed things up, save memory, and you name it there. This is just one use case we picked to say, let's go into dive and say, here's how we did this and the technology we use there. I think we're using Hazelcast, we're using Redis, we're using Ignite here. We have EH Cache in play. We have them all in play, I think, across the system there. We've been using EH Cache for a number of years just to keep things in the local memory. Redis went in to cache the claims in our system last year. That worked well. Now that I know a lot more about Redis, I might have went with Redis in this solution. It's probably simple for that one. Hazelcast we're using a lot in the back end we're looking at. So we're exploring a lot of the options in the industry right now. This is one, we were at, said, let's try this one, let's try this one, let's try this one, until we found something that we felt was work with. I felt that this was a doable solution, that we can get to something that will work and get us to 90,000. Banging our brains at the database just didn't make any sense for sequencing. The algorithms we're using were good, I thought, but just killing ourselves going to the database when it's a small set of data, really. These active guys shouldn't be too big, and once in a while to grow. I thought we could solve that. Good question.
And session clustering is another thing we are looking for distributed caching. So we have a legacy system. So what happens? We have sessions kept in JVM. When one request goes from one JVM to another JVM because of routing or something, now we use sticky session. If it goes to another JVM because of stickiness we remove, it fails. So we are thinking about moving them to.
Yeah, that's a good use case in a registration workflow. As you check in, you collect the name, the insurance, all that information. We have you going back to the same JVM and holding on to that memory until you finally finish that conversation. Say, okay, I'm done. Save that guy. I'm checked in. Well, for any use case where that JVM would fail, man, we lose that data in memory. So we've been thinking about, it would be a lot better to say, as we get that data, just save it somewhere so that you can, if we failed, you can come back up on another JVM, or even better, if you hit that one JVM for the first part of the conversation, just go anywhere for the second part of the conversation. Don't go back to that sticky session. We've been working on that. But yeah, we have tons of use cases to improve, to be honest.
The previous one?
Yeah,
The big one with all the stuff moving on? Oh yeah, the lively one?
So in terms of bottlenecks, have you done unit level test to find out what are the maximum throughputs you can have at every layer? Because obviously...
This one you're talking about?
Yeah.
I would say yes. We measured that and said, where's the bottleneck? This data here, the transformation, if we scaled it out, how fast you go there. But the more we scaled that out, how fast it would run there. The problem was that as the sequencer ran and got a record in there and recorded that in the database and said, okay, here's a record to process and whatnot, and they were coming in, and it had a lot of them running through, and then we scaled out the adapter to do the transformation. Eventually, that was the bottleneck and slowed down. He wasn't passing enough data to those OpenLink adapters to do work. They were starving because they weren't getting enough work to do. So that's how we identified the bottleneck there. So and then we go back and say, okay, what's the capacity of the sequencer to process and do records there? What's the capacity of our OpenLink adapter? What's our capacity of our JMS? The pieces there. But we had to put the whole thing together and really see which one was ending up killing us. But from the get-go, I thought, this is probably where we're going to have a problem at the sequencer area there.
Do you have to actually use these queues that you have? Because you can use stream processors.
Yeah, there's lots of options there. We're a JMS shop. We've been using JMS for a number of years. We're pretty good at JMS,
we have
we choose
different,
that.
even some open source one also.
Yeah.
So we have different frameworks, like for aggregator splitter framework, we call it action request processing, which just actually sprays message to different JVMs instead of pushing things. JVMs pull things, and then when processing is done, we aggregate things, which is kind of MapReduce of Java side using JMS. So many things we do.
Yeah, but we've been building this for a while. So we went over to Java JMS 2010, 2011, 2012. We went a lot into that, and pretty happy with the JMS there. And we actually just started using streams inside the program a lot. I just found last week our front end. Users wanted to get this claim produced, a claim validation done really quick to tell them if this data was going to be okay to edit there. And it was little claim validation was taking us maybe about 5 seconds to run it through the back end of the system that runs at night, and said, boy, how do we get that down to 1 second? And we actually put a Redis cache in front of that and said, listen, if you come in and you hadn't changed there, we'll give you back the same answer you got last time. And if you change, we'll only do the edits on the fields that change. So we sped that up to 1 second. And I said, that's wonderful. And then I said, well, by the way, we have these certain patients in here that come in every day, and they have 30 days, and you have to do 30 claims on that guy and bring it back in 1 second. So, okay, so let's throw a parallel stream on there. We flipped the code, we put a parallel stream on there and said, okay, we'll do 30 of them at the same time and see how it goes. And we just finished testing that this week, and it's looking okay. And that's inside one JVM, and I think, we're debating whether we want to keep it in one JVM or do we want to fan it out to multiple JVMs, because that's a lot of inside one JVM to do. But
have you explored like off-heap within the VM?
no, but I just heard about that today. So, with the guy from the Swedish guy talking about the off-heap stuff. So, yeah, I'm always into it. I love performance changes. So, that's why I like coming to this stuff, to look at different ways of doing it. Yeah, to make it quicker. Yeah, the one thing I do enjoy about this healthcare environment, there's a lot of opportunities to do the work and make it better. Yeah, good question. Thank you. Okay, guys, it's the weekend. We're done for, I'm going home tomorrow, so it's my weekend. I'm out of here. Yeah. Thank you very much.